Welcome! In this video, we'll dive into problem number 18, for sum, where we explore how to find all unique quadruplets in an array that sum up to a target value. Let's break down the problem, analyze approaches, and solve it step by step. Stay tuned! In this problem, we are given an integer array nums of length n and an integer target. The goal is to find all unique quadruplets, A, B, C, D, in the array such that their sum equals the target value. Specifically, the condition is that A plus B plus C plus D must equal target. Additionally, the quadruplets should be listed in ascending order, and there should be no duplicate quadruplets in the output. It's important to note that the final list of quadruplets can be returned in any order. For the input, nums is a list of integers with a size between 1 and 200, and target is a single integer. The output will be a list of lists, where each inner list contains exactly 4 integers that satisfy the condition of summing to the target value. Let's look at some examples to understand this better. In the first example, the input array is nums equals 1, 0, minus 1, 0, minus 2, 2, and the target value is 0. The output is a list of 3 quadruplets, dash 2, minus 1, 1, 2, dash 2, 0, 0, 2, and dash 1, 0, 0, 1. Each of these quadruplets adds up to the target value of 0. For instance, in the first quadruplet, dash 2 plus minus 1 plus 1 plus 2 equals 0. While the indices of these numbers in the original array may vary, the key is that their values satisfy the condition. Also, notice that the quadruplets are listed in ascending order, and there are no duplicates among them. Now, in the second example, the input array is nums equals 2, 2, 2, 2, 2, and the target value is 8. Here, the output contains only one quadruplet, which is 2, 2, 2, 2. This is because the sum of the 4 2's equals the target value of 8. There are no other combinations in this array that satisfy the condition, and since all elements are the same, the result is naturally unique. This highlights how the solution needs to handle arrays with repeated values while ensuring that no duplicate quadruplets are included in the output. In the third example, the input array is nums equals 1, minus 2, minus 5, minus 4, minus 3, 3, 3, 5, and the target value is dash 11. The output here is a single quadruplet, dash 5, minus 4, minus 3, 1. This is the only combination of 4 numbers in the array that adds up to the target value of dash 11. Once again, the quadruplet is listed in ascending order, and no duplicate quadruplets are included. Alongside the examples, we are also given some constraints to keep in mind. The length of nums can range from 1 to 200, and the values in nums as well as the target can be very large, ranging between dash 10⁻9 and 10⁻9. This means the solution needs to be efficient enough to handle large input sizes and values. Finally, let's consider some edge cases that might arise when solving this problem. First, if the input array nums has fewer than 4 elements, it's impossible to find a quadruplet, so the output should simply be an empty list. Second, if all elements in the array are the same, such as nums equals A, and 4 asterisk A equals the target, the output should include just one quadruplet, A. Third, if no valid quadruplets exist, like in the case of nums equals 1, 2, 3, 4, with target equals 100, the output should also be an empty list. Lastly, the solution must ensure that duplicate quadruplets are not included in the output, even if the input array contains repeated numbers. This involves careful handling of duplicates during the computation process to produce the correct result. To solve the for-sum problem, we first consider the brute force approach. The idea here is straightforward: generate all possible quadruplets from the input array nums, check if their sum equals the target value, and ensure that the quadruplets are unique. To enforce uniqueness, we can sort each quadruplet before adding it to the result set. However, while this method is simple to understand, it is computationally expensive. The time complexity is n to the power of 4, as we are iterating over all possible quadruplets, and the space complexity is n, accounting for temporary storage during sorting and result storage. This inefficiency becomes apparent as the size of the input grows, making the brute force approach impractical for larger inputs. To address these limitations, an optimized approach can be employed, which leverages sorting and the two-pointer technique to significantly reduce the number of combinations we need to evaluate. The optimized approach begins by sorting the input array. Sorting serves two purposes. It simplifies the handling of duplicate values and enables the use of the two-pointer technique. Once the array is sorted, we use two nested loops to fix the first two numbers of the quadruplet, denoted by indices I and j. For the remaining two numbers, we apply the two-pointer search, where one pointer starts just after j and the other starts at the end of the array. By adjusting these pointers based on the sum of the four selected numbers, we can efficiently find valid quadruplets. To ensure uniqueness, we skip over duplicate values for all indices involved, I, j, left, and right. Additionally, we use early termination to optimize further. For instance, if the sum of the smallest possible quadruplet exceeds the target, or the sum of the largest possible quadruplet is less than the target, we can terminate the search early for that configuration. This approach improves the time complexity to O(n cubed, dominated by the three nested loops, while the space complexity remains O(1) for in-place operations. By eliminating unnecessary combinations, we achieve a significant improvement over brute force. The chosen strategy for solving the four-sum problem is the optimized approach that combines sorting with the two-pointer technique. This method strikes a balance between performance and simplicity, making it well-suited for larger input sizes. Key observations underline the effectiveness of this strategy. First, sorting the array upfront is crucial, as it simplifies handling duplicates and facilitates the two-pointer traversal. Second, the use of early termination adds efficiency, as we can prune the search space whenever the current configuration is guaranteed to fail. Finally, the two-pointer technique itself is highly efficient, reducing the problem's complexity from O(n to the power of 4) in brute force to O(n cubed). This approach excels because it is significantly faster than brute force for larger inputs, while maintaining simplicity and scalability. However, there are trade-offs to consider. While the memory usage remains minimal, sorting the array adds an O(n log n) pre-processing step. Nevertheless, this overhead is negligible compared to the overall time savings achieved in the main computation phase. In conclusion, the optimized approach, which uses sorting and the two-pointer technique, is the most practical and efficient solution to the four-sum problem. This method effectively balances the trade-offs between computational efficiency, simplicity, and scalability, making it a robust choice for handling even larger input sizes. The problem we're addressing here is to find all unique quadruplets in an integer array that add up to a given target. To approach this, we first sort the input array. Sorting is crucial because it allows us to efficiently handle duplicates and leverage the two-pointer technique later in the algorithm. Sorting the array can be done using an algorithm like quicksort or mergesort, both of which operate in O(n*log n) time complexity. Once the array is sorted, we then fix two elements using nested loops. The outer loop selects the first element, starting from index 0 and running until n4, ensuring that there are at least 4 elements to form a quadruplet. The inner loop selects the second element, starting just after the first, up to n3. By fixing these two elements, the problem reduces to finding two more numbers in the remaining part of the array that sum up to the adjusted target, which is target nums I, nums j. This reduction simplifies the problem significantly and sets up the groundwork for the two-pointer search. With the two elements fixed, we now use the two-pointer technique to find pairs in the remaining array. The left pointer is initialized to the position right after the second fixed element, and the right pointer starts at the end of the array. While the left pointer is less than the right, we calculate the current sum of the quadruplet formed by the fixed elements and the elements at the left and right pointers. If this sum matches the target, we add the quadruplet to the result list and move both pointers inward to explore other potential pairs. If the current sum is less than the target, we move the left pointer to the right to increase the sum. Conversely, if the current sum is greater than the target, we move the right pointer to the left to decrease the sum. To ensure uniqueness, we skip over duplicate values after moving the pointers. This step is made efficient by the initial sorting of the array, which groups duplicates together, allowing us to bypass them easily. Finally, once all valid pairs are found for the fixed elements, we proceed to the next iteration of the loops. The algorithm relies on several key insights to achieve its efficiency. First, sorting the array simplifies the handling of duplicates, as consecutive duplicate values can be skipped during iteration. This ensures that only unique quadruplets are included in the result. Second, the two-pointer technique is a significant optimization over a brute force approach, which would involve 4 nested loops and result in much higher time complexity. By reducing the problem to finding pairs, we streamline the process and avoid unnecessary computations. Third, the algorithm incorporates efficient pruning. For example, if the current sum exceeds the target, we terminate the loop early, knowing further iterations will only increase the sum. This avoids redundant calculations. Additionally, edge cases like arrays with fewer than 4 elements are handled gracefully by immediately returning an empty list. The algorithm also accommodates arrays with negative numbers and duplicate values, as the sorting step and duplicate checks ensure correctness regardless of input composition. The result list stores the unique quadruplets, which are derived from the sorted array, ensuring both accuracy and efficiency. Now let's break down the complexity of the algorithm. Sorting the array initially takes n*log n time. Next, the 2 nested loops for selecting the first 2 elements contribute an n² factor. Within these loops, the two-pointer search runs an n for each pair of fixed elements. Combining these factors, the overall time complexity is n*log n plus n cubed, where the cubic term dominates for large inputs. As for space complexity, the algorithm operates in O1 additional space since the sorting is performed in place, and no extra data structures are used beyond the result list. To clarify this approach, let's consider an example. Suppose the input array is 1, 0, -1, 0, -2, 2, with a target of 0. By following the algorithm's steps, we'll systematically find all unique quadruplets that meet the criteria while adhering to these complexity bounds. Let's walk through the execution of this example in detail. First, we sort the array, resulting in -2, -1, 0, 0, 1, 2. We then fix the first element, I equals 0, making nums, I equals -2. Next, we fix the second element, j equals 1, making nums, j equals -1. The left pointer starts at index 2, and the right pointer starts at index 5. Calculating the current sum, -2 plus -1 plus 0 plus 2, gives -1. Since this is less than the target, we move the left pointer to index 3 and recalculate. This time, the sum equals 0, so we add the quadruplet, -2, -1, 0, 2, to the result. After adding it, we skip over duplicates for both the left and right pointers, ensuring no redundant quadruplets are included. Repeating this process for other combinations, we eventually derive the complete result, -2, -1, 0, 2, -2, 0, 0, 1, -1, 0, 0, 1. This demonstrates how the algorithm efficiently identifies all unique quadruplets while avoiding unnecessary computations. Here, we start by defining a class-named solution with a method forsum that takes 2 parameters, nums, which is the input list of integers, and target, the target sum we want to achieve. The first step is to sort the nums array, as this will help us efficiently handle duplicates and implement the two-pointer approach later. We also initialize n to store the length of the array and an empty list called result to store our final quadruplets. Next, we use a nested loop structure to iterate through the array. The outer loop begins with the variable I, representing the first index of the quadruplet. To avoid processing duplicate values at this level, we check if the current number at I is the same as the previous number and skip it if it is. Similarly, the inner loop uses j to represent the second index of the quadruplet. Again, we include a condition to skip duplicates at this level as well. After setting up these 2 loops, we proceed to implement the two-pointer approach for the third and fourth indices, using variables left and right, starting right after j and at the end of the array, respectively. Within this two-pointer loop, we calculate the current _sum by adding the values at I, j, left, and right. If this sum matches the target, we append the quadruplet to the result list. To handle duplicate values for the third and fourth indices, we move the left pointer forward while the next value is the same as the current one. We continue by ensuring that after handling duplicates for the third index, the left pointer is incremented again to move to the next unique value. Similarly, to handle duplicates for the fourth index, we move the right pointer backward while the previous value is the same as the current one. After handling these duplicates, we increment left and decrement right to continue searching for other potential quadruplets. If the current _sum is less than the target, we increase the left pointer to try to make the sum larger. Conversely, if the current underscore sum is greater than the target, we decrease the right pointer to reduce the sum. This process continues until the left and right pointers cross each other, at which point we break out of the two-pointer loop and proceed with the next iteration of the inner and outer loops. Once all possible quadruplets have been evaluated, the method returns the result list containing all unique quadruplets that sum up to the target value. This implementation ensures efficiency by leveraging sorting, duplicate checks, and the two-pointer approach to minimize unnecessary computations. Here, we begin by importing the necessary Java utilities and defining the class solution. Inside it, we create the foresum method, which returns a list of unique quadruplets from an integer array that sum up to a given target. First, we initialize an empty list called result. If the input array is null or has fewer than 4 elements, we immediately return the empty result since it's impossible to form a quadruplet in such cases. Next, we sort the array to simplify the process of identifying and skipping duplicates. Sorting also helps optimize the two-pointer approach that we'll use later. We then start with the first for loop, iterating through the array with index I. Here, we ensure that if the current element is the same as the previous one, we skip it to avoid duplicate quadruplets forming. Similarly, the second for loop, with index j, starts right after I and follows the same logic to skip duplicates for the second index. After setting up these two loops, we initialize two pointers, left and right, which will help us efficiently search for the third and fourth numbers in the quadruplet. Using the two-pointer approach, we calculate the current sum by adding the values at indices I, j, left, and right. To avoid integer overflow, we cast the sum to a long. If this sum matches the target, we add the quadruplet to the result list. To handle duplicate values, we adjust both left and right pointers. Specifically, while the value at left is the same as its next value, we increment left, and while the value at right is the same as its previous value, we decrement right. This ensures that we skip over any repeated values to avoid duplicate quadruplets in the result. After handling duplicates, we move both pointers inward to continue searching for other potential pairs. If the current sum is less than the target, we increment the left pointer to increase the sum. Conversely, if the current sum is greater than the target, we decrement the right pointer to reduce the sum. This process continues until the left pointer meets the right pointer, signaling that all potential pairs for the current indices I and j have been checked. Finally, after iterating through all possible combinations of indices and ensuring that duplicates are skipped, we return the result list containing all unique quadruplets that satisfy the target sum condition. This marks the end of the foresum method and completes the implementation. By using sorting and the two-pointer approach, we ensure an efficient solution for this problem, significantly reducing the number of combinations we need to evaluate. To solve the foresum problem, we start by considering the first example, where the input array is 1, 0, -1, 0, -2, 2, and the target is 0. The first step is to sort the array, which gives us -2, -1, 0, 0, 1, 2. This makes it easier to apply the two-pointer technique later. We also initialize an empty list result to store any quadruplets we find. Now, we begin iterating through the array. For the first loop, we set I equals 0, which corresponds to the value -2. Since there's no previous I to compare against, we skip the duplicate check. Next, we move to the second loop, setting j equals 1, which corresponds to -1. Again, there's no previous j, so we skip the duplicate check here too. With I and j fixed, we initialize two pointers, left at index 2 and right at index 5. Using these pointers, we calculate the sum of the four values. Initially, the current underscore sum is -2 plus, -1, plus 0 plus 2 equals -1, which is less than the target. To increase the sum, we move the left pointer to 3. The sum is still -1, so we move left again to 4. Finally, the current underscore sum becomes -2 plus, -1, plus 1 plus 2 equals 0, which matches the target. We append this quadruplet, -2, -1, 1, 2, to our result and skip any duplicates before updating left to 5 and right to 4, which ends this iteration of the two-pointer approach. Now, we continue with the second loop by incrementing j to 2, which corresponds to 0. With I still at 0 and j at 2, we initialize left at 3 and right at 5. This time, the current underscore sum is -2 plus 0 plus 0 plus 2 equals 0, which matches the target. We append -2, 0, 0, 2 to our result. After skipping duplicates, we update left to 4 and right to 4, ending this iteration of the two-pointer approach. Next, we increment I to 1, which corresponds to -1, and proceed with the first loop. Since there are no duplicate values to check against, we move to the second loop. At this point, the final result for this example is -2, -1, 1, 2, -2, 0, 0, 2. Moving on to the second example, the input is 2, 2, 2, 2, 2, with a target of 8. After sorting, the array remains 2, 2, 2, 2, 2. We initialize an empty result list and set I equals 0, which corresponds to 2. Since there's no previous I, we skip the duplicate check and proceed to the second loop. In the second loop, we set j equals 1, which also corresponds to 2. Again, there's no previous j, so we skip the duplicate check. We then initialize left at 2 and right at 4. Using the two-pointer approach, we calculate the current underscore sum, which is 2 plus 2 plus 2 plus 2 equals 8. This matches the target, so we append 2, 2, 2, 2 to the result. To avoid duplicates, we skip over all duplicate values for both left and right, updating left to 5 and right to 3. At this point, the pointers cross, ending the inner loop. Since there are no other combinations to explore, the final result for this example is 2, 2, 2, 2. In the third example, the input array is -3, -2, -1, 0, 0, 1, 2, 3, with a target of 0. After sorting, the array remains -3, -2, -1, 0, 0, 1, 2, 3. We initialize result equals, and set I equals 0, which corresponds to -3. There are no duplicates for I, so we move to the second loop. In the second loop, we set j equals 1, which corresponds to -2. Here, we initialize left at 2 and right at 7. Using the two-pointer approach, the current underscore sum is first calculated as -3 plus, -2, plus, -1, plus 3 equals -3, which is less than the target. To increase the sum, we move left to 3. The next current underscore sum is -3 plus, -2, plus 0 plus 3 equals -2, so we move left again to 4. Repeating this process, the sum remains below the target until left reaches 6. At this point, the current underscore sum becomes -3 plus, -2, plus 2 plus 3 equals 0, which matches the target. We append -3, -2, 2, 3 to the result. After this, we continue iterating through other values of I and j to find additional quadruplets. The process involves skipping duplicates and adjusting the two pointers as needed. By the end of the computation, the final result contains several valid quadruplets, such as -3, -2, 2, 3, -3, -1, 1, 3, -3, 0, 0, 3, representing all unique combinations that sum to the target. To analyze the time complexity of the foursome algorithm, we start with sorting the input array. Sorting takes O, n asterisk log, n, time, where n is the size of the array. Next, the algorithm uses two outer loops, with the first loop iterating from 0 to n3 and the second loop iterating from I plus 1 to n2. Each of these loops independently runs in O, n, time, and together, they result in O, n squared, iterations. Within each iteration of the nested loops, we apply a two-pointer search to find pairs of numbers that sum to the target. The two pointers traverse the remaining segment of the array, which has at most O, n, elements, leading to O, n, time for this step. Combining these components, we can now move forward to compute the overall time complexity. Now, putting all the steps together, sorting the array takes O, n asterisk log, n, the two nested loops contribute O, n squared, and the two-pointer search adds an O, n, term for each iteration of the inner loop. Multiplying these terms, we get a total time complexity of O, n asterisk log, n, plus O, n squared asterisk n, which simplifies to O, n cubed, in the worst case. Shifting focus to space complexity, the algorithm sorts the array in place, which uses O, 1, additional memory. The result list stores all unique quadruplets found, and in the worst case, this could grow up to O, n to the power of 4, if all combinations are valid. Additionally, the algorithm uses a constant amount of memory for variables like I, j, left, right, and other intermediates, contributing O(1). Thus, while the algorithm itself uses O(1) space, the overall space complexity is dominated by the result storage, which can reach O(n) to the power of 4 in extreme cases. Let's compare this approach to a brute force method. In a brute force solution, we would generate all possible quadruplets from the array and check their sums. The number of quadruplets for an array of size n is O(n) to the power of 4, and since checking the sum of each quadruplet takes O(1), the total time complexity of brute force is O(n) to the power of 4. The foursome algorithm optimizes this significantly. By sorting the array in O(n*log n, and combining two nested loops with a two-pointer search, we reduce the number of combinations to check. This results in a time complexity of O(n³), which is a substantial improvement over O(n) to the power of 4, especially for larger input sizes. Now, considering the best, average, and worst-case scenarios, the best-case time complexity remains O(n³), as the algorithm iterates through all valid quadruplets even if the array is small or an early termination condition is added. In the average case, the algorithm typically processes O(n³ combinations, depending on the distribution of numbers in the input. For the worst case, with a large array containing many valid quadruplets, the algorithm still runs in O(n³ time. Additionally, the output size could grow up to O(n) to the power of 4 if there are an exceptionally high number of valid quadruplets. To mathematically summarize, the dominant term in the time complexity comes from the nested loops in two-pointer search, which scale as O(n³). Sorting, at O(n*log n), becomes negligible for large n. For space complexity, while the algorithm itself uses O(1), the result storage can grow to O(n) to the power of 4, depending on the input, which is a significant limitation of the approach. When tackling the foursome problem, there are several common mistakes to watch out for. First, not handling duplicate quadruplets can lead to redundant results. Sorting the array initially and using pointers to skip over duplicates is an effective way to ensure each quadruplet is unique. Another frequent issue is relying on inefficient brute force approaches. Generating all possible quadruplets results in an O(n) to the power of 4 time complexity, which is impractical for larger inputs. Instead, optimize your solution with sorting and two-pointer techniques to minimize unnecessary computations. Additionally, edge cases are often overlooked. Scenarios like arrays that are too small, contain negative numbers, or involve large target values can lead to incorrect or inefficient results. Explicitly handling these edge cases is essential. Incorrect pointer updates are another pitfall. Failing to adjust pointers properly, especially when skipping duplicates, can cause infinite loops or missed solutions. Lastly, in languages like C++, be cautious of integer overflows when summing large numbers. Using appropriate data types or modular arithmetic can help prevent these issues. Now, let's consider some valuable insights for interviews. Recognizing the foursome problem as a variation of the k-sum pattern is key. If you're comfortable with simpler cases like two-sum or three-sum, extending these approaches to four-sum becomes much more intuitive. The optimal solution involves sorting the array and combining nested loops with a two-pointer technique. This reduces the time complexity from O(n) to the power of 4 to O(n³), making it feasible for larger datasets. Importantly, during interviews, always discuss the trade-offs between brute force and optimized approaches. This demonstrates a strong grasp of time and space complexity. Additionally, interviewers often test edge cases, such as empty arrays, arrays with all identical elements, or very large target values. Being prepared to address these scenarios will showcase the robustness of your solution. The foursome problem is closely related to several other LeetCode problems, which can help you build a deeper understanding of the k-sum pattern. Two-sum, for instance, is the simplest form of this family and is excellent for practicing hash map-based optimizations. Three-sum is a direct precursor to four-sum, focusing on reducing complexity using sorting and two-pointer techniques. For added complexity, three-sum closest challenges you to find the sum closest to a target, making it a great exercise for edge case handling. Lastly, the generalized k-sum problem extends the approach to any dimension, helping you adapt and scale your solution methodology. Finally, let's explore some alternative approaches to solving the foursome problem. The hash set method involves storing pairs of numbers in a hash set and checking for complements. While this can reduce redundant computations, it does require additional space. Another option is the recursive k-sum approach, which generalizes the solution for any k. This method is flexible but can be more challenging to implement and debug, especially under time constraints. The meet-in-the-middle strategy is another powerful technique. By dividing the array into two halves, calculating all possible pair sums for each half, and then combining results using a hash map, this approach can be effective for larger arrays but demands careful implementation. Ultimately, mastering foursum equips you with a solid foundation in the k-sum pattern, a common topic in coding interviews. Focus on optimizing your solution to O(n)³ with sorting and two-pointer techniques, and always be ready to address edge cases and discuss trade-offs. Great job! Today, we tackled the foursum problem, reviewed strategies from brute force to optimized solutions, and highlighted useful techniques like sorting and two-pointer methods. Remember to keep practicing and applying these concepts to similar problems. Thanks for watching. Don't forget to like, subscribe, and join us for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!